earlier talks. Then I'll talk very briefly about what the Nirvana platform is, and it might provide some motivation as to how we designed Neon and why we designed it in the way that we did. And then sort of bulk of the talk will be hands-on exercise on building a sentiment analysis model. And there'll be a demo of this kind of model that can play video games. Some of you might have seen this demo from DeepMind, where you can train a model to play Pong and Breakout and all these different Atari video games. So recently, one of the external contributors to Neon came up with this, so I'll showcase that as well. And finally, I'll say a little bit about where we're heading with the Nirvana cloud. So to quickly go through, since I think when it was asked earlier how many people had kind of used deep learning, only 20% of the people raised their hands here. So I'll just start with a quick intro. So deep learning is a method for extracting features directly from the data with multiple levels of abstraction. The thing that kind of differentiates it from many other techniques is that before deep learning became really big, we used to try and learn features, like human beings used to provide the features that would go into these deep learning models. Whereas now you can set up these kind of end-to-end pipelines that can do both the feature learning as well as the classification within this one big pipeline. And some of the power of deep learning comes from it being able to learn really complex features and learn really complex representations through these multiple layers. So to sort of just go through the basics of one of these networks that's been really successful, the convolutional neural network. So here you see that there's a picture of a cat or a speech signal that's being fed into the network. And then you have these different layers in, let's see if there's a, oh, okay. I was just wondering if there's a pointer here, but that's fine. So each of these rectangular boxes is one of the layers of the network, and there are these parameters that connect the different layers called weights. And through the training process, you're learning what the correct weight should be to go from something like the raw image or the raw speech signal to a label of a cat or what the text of that speech signal is. And then once this training is complete, you can kind of probe each of these layers and try to figure out what those parameters mean. So there are some techniques to do that, and when you apply those techniques, you sort of see that the lower level layers have learned these oriented bars, whereas layers further up have learned shapes or even things like faces of cats and dogs. And this kind of has an analog in the brain that if you go into primary visual areas, you see that neurons respond to things like this, whereas if you go to higher level visual areas, they respond to things like faces and more complicated shapes. So there's a sort of very high level similarity between things that the brain learns to represent and things that a neural network learns to represent. And as you can see here, there's both feature learning as well as the classification at the end happening in this one long pipeline. So you don't need these different systems like you used to before for learning the features and then doing classification using a separate algorithm. So quickly, why is there so much excitement about deep learning? It's basically about performance. Until about 2011, people were using sort of pre-deep learning kind of methods in computer vision for this ImageNet competition. And then in 2012, this new approach from Krzyzewski and others came on the scene. And it's really revolutionized this field as well as others. and recently sort of coming close to or even surpassing human-level performance for this task. So in the next 3 slides, I'll just go through some really sort of high-level examples of how of the power of deep learning and what it can be applied to. So this is an example from Jan LeCun, where you'll see a person riding a bike around in New York, and in sort of real time, the scene will be classified into its different constituent elements. So below is the image that the camera on the bike rider's helmet sees, and then up above you can see that the different constituents of the scene, like the road, the wall, trees, are being segmented out. So this was using a convolutional neural network. Another example is in the domain of speech. So Skype recently introduced this feature where you can talk in one language, and in real time, it'll sort of translate into a destination language. So here you'll see an example from Skype of a person speaking in German and the person on the other end hearing the translated sentence in English. Oh, no sound. Yeah.
Einen helleren Farbton ändern.
Ja, wir können das Grün viel heller machen.
Yes, we can make the green much brighter.
Ich sende dir heute Abend eine neue Datei.
I'm sending you a new file tonight.
That sounds great. I look forward to it. Das klingt.
All right, so hopefully some of you could hear that. And then another example was from Andrei Karpathy and others. Actually, there were other labs around the same time that had similar results, but it was basically taking images and not just inferring that there's a cat or a dog or a unique object category in the picture, but being able to write a full caption for it. So these were pretty detailed captions. Like you can see that it shows that it's not just a man or a guitar, but it's a man in a black shirt playing guitar. So as a data scientist, depending on the type of application that you're going for, you might want to choose a particular kind of deep learning approach. And so on the left here are sort of some of the deep learning approaches that have been used. And on the right are the corresponding problems for which they're typically used. So just like I mentioned, for anything to do with image localization or classification, you might use a convolutional neural network. So there's things, so these models called RBMs, restricted Boltzmann machines, they were really big a couple of years ago. They were applied to things like drug targeting and collaborative filtering kind of problems. So this was one of the components of the winning entry for the Netflix prize. And in general, they can be used for imputing any kind of missing interaction. So if you have missing data. So recurrent neural networks, people have mentioned today, anything to do with time series or sequence kind of data sets, they're used quite often. So for things like speech, translation, they can be applied. And multi-layer perceptron is sort of I would call it the vanilla neural network. It's sort of just taking a bunch of perceptrons, putting them together into a layer, and then stacking them up. So these can be applied to kind of arbitrary input-output kind of problems if you don't know that a priori what the structure looks like. Is it an image or a time series problem? If it's just a table, then you might want to just apply a multi-layer perceptron approach to it. And then finally, this deep Q networks are used for reinforcement learning, sort of like the video game playing example that I was mentioning earlier. So again, I think in the previous talk, there was quite a bit about recurrent neural networks. I can go through it pretty quickly. So you have, the idea is that you have a multi-layer perceptron, which is basically a bunch of perceptrons linked together into a layer. And then in this case, you have 3 layers, input, hidden, and output. And for a recurrent neural network, you create these connections, which for the hidden layer, they also receive input from the previous time point. And when you're training such a network, you can basically unroll it so it looks like a multi-layer perceptron, and then you can just apply backprop in order to train it. And so a related approach to that is this long short-term memory where you now take that one perceptron-looking cell and you make it a little bit more complicated. You add a few gates inside the cell, and these can help you kind of tune parameters that can adjust how long you want to remember something for. So this was also covered in quite a bit of detail in the previous talk, so I can just go through it pretty quickly. I think one thing that's kind of interesting is that you can actually mimic the behavior of a standard recurrent neural network using these, but in addition, learn more complex time series relationships. So later on in the talk, for the hands-on example, we'll be using LSTMs to do sentiment analysis. So we'll be looking at a IMDb data set and learning to predict what the numerical rating would be based on the text of the review. But these kind of models have been applied to state-of-the-art results in machine translation, video recognition, speech recognition, and caption generation. So just quickly want to mention a little bit about our platform in the context of how Neon has been designed. So what we're trying to build is basically a cloud service that makes it really easy for data scientists to train the models, do exploration, and then deploy those models. And so Neon is sort of built as a framework that can be downloaded and installed locally on your machine. But if you want to scale up, then you can sort of change one line of code and then run that on a cloud. And it's sort of, the cloud part is seamlessly integrated with other cloud providers like AWS. And sort of underlying the cloud is the hardware is abstracted out. So you can just write your code once and run it on CPUs or GPUs today. Or you can run it on this thing we call the Nirvana engine, which is a new kind of distributed deep learning processor that we are aiming to provide an order of magnitude speed up with. So we see deep learning as a core technology. If you work at Google, you have the luxury of using this thing called the Google Brain, and teams within Google can sort of design their machine learning model using this as a platform. So with the Nirvana platform, we're trying to bring that level of scale and speed to everybody else. So you can basically use our platform to build these different capabilities like image classification, localization, speech, sentiment analysis, video indexing, or machine translation. So our core technology, as I mentioned, is the Nirvana engine, within which we have this unprecedented compute density. It's built for a distributed architecture, so that relates to some of the things in our framework. It's built for distribution, and it's built for both learning and inference. And the architecture that we're building for our hardware is really optimized for deep learning. So we really wanted to build something for the deep learning community. So you have something that's built from the ground up just for deep learning. So the instructions at a fundamental level are going to relate to deep learning. So we've used Neon for many different verticals. We've solved problems in finance for looking at fraud, for example. We've worked with some companies in the medical space, looking at both medical imaging applications as well as doing NLP on patient records. We worked a little bit in the pharma space. In oil and gas, we've looked at seismic data and sort of determined using these convolutional networks what are the areas that are rich in oil. In the agricultural space, we worked in both in robotics as well as in precision agriculture kind of applications. and then internet and also with some government agencies. Right, so now, any questions so far? Or well, hopefully that was some introduction. So now I'm actually going to dive into Neon a bit and give a little bit of an intro into Neon itself. So Neon is designed to be user-friendly, extensible, and we abstract out the parallelism and data caching. We have built-in support for many of the common models in the examples. Like if you have the AMI, you can look at the examples and you'll see that many of the cases that I mentioned earlier are as examples in that folder. It provides this interface to the cloud, supports multiple hardware backends. It's currently optimized for the Maxwell GPU architecture, right down to the assembler level. And there's support for basic automatic differentiation. So when people are coming up with new kinds of layers, they often want to experiment with many different forward propagation functions and then automatically get the backprop. And for a while, you had to sort of manually write the backprop in Neon, whereas things like Piano, you can automatically get the backprop function. So recently, we added some basic capabilities that you can specify an fprop function for a layer and then just call a dot bprop on that to get your backprop. And it's open source under an Apache 2.0 license. So you can basically train your models, and with some of our customers, they have a deployed kind of use case. So if you want to run it like on a tractor or something like that, you can go ahead and do that. So at a high level, it's object-oriented design. There's decent amount of documentation on neon.nirvanasys.com, so I encourage you to check it out. And so some of the components that we provide are things like the backend. So we provide the capability to run on CPU, GPU, or a hardware, but the hardware part is still an internal use only. There's some standard data sets that you can use, like ImageNet, CFAR10, MNIST for images, Flickr and Coco for captions, PenTreeBank, Cutterprise, IMDb, and soon this Amazon dataset for sentiment analysis. We have the common initializers. So when you're training these models, the weights are typically initialized according to some distribution. So we have constant, uniform, Gaussian, and Glorot. All the common learning rules, which you've been hearing about all day, like stochastic gradient descent, RMS prop, eta delta, atom, eta grad. Common activation functions, layers for convolution, deconvolution, and the constituent layers for recurrent networks. The different cost functions, so binary cross entropy, multi-class cross entropy, and sum of squares error. And metrics, classification, misclassification, which can also be extended to top K misclassification, and accuracy. So this is a basic model. This is a multi-layer perceptron. We start off with defining some kind of data set in this data iterator, and then we have the initialization of, in this case, a Gaussian centered at 0 with standard deviation 0.01. And then this model is pretty simple. It just has a couple of layers. Both are these affine layers, and one has 100 units, the other has 10 units. We build a model, assign a cost to it, and call an optimizer. And then when you call fit, it runs the model. So how many people are actually following along with the AMI? 5 people? Okay, so is it okay? Should I skip the AMI or? Okay, maybe I'll just demo it, and if people want to follow along, they can. So let me. Okay. Okay, so this is the multi-layer perceptron example. It's sort of similar to the one that I had on the slide earlier. It has those two affine layers. And just to give you a sense of what that looks like when I want to train it, so let's just call so here just displays a summary of what the architecture of the network looks like. So it's basically with 784 inputs, and then that's the size of the image for this MNIST data set. And it has another hidden layer with 100 units, and then the output has 10 units in this case, because you're classifying digits from 0 to 9. So as it ran really quickly in this case, but you could basically see the progress bar kind of going forward as the training progressed for each epoch. It shows you what the cost is as it's training, but then after each epoch as well. And at the end of it, it shows you the misclassification error. So this is basically the usual kind of workflow for training would be that you would run this kind of executable script that has the specification of your model and the optimizer and these sort of different building blocks that go into constructing your neural network. So in Neon, we have another sort of more compact way of defining a model. So you can take everything that was in a Python script and make it into YAML, which is like basically a high-level plain text kind of format. And so you just specify your cost, how many epochs you want, the batch size, and then for each of those things that I mentioned earlier, you can just write down this very compact file that you can use to specify your layer types and how many units you want in them and all the different parameters that were there. And basically, you can run this with a bin neon executable. So now instead of the Python file, I'll be running the YAML file. So yeah, it's basically running the same model as earlier. So that's just to give a flavor of what a Neon script looks like, what the YAML looks like, what the training process looks like. So just go back to the presentation. So just like the MLP example, there's also a pretty basic RNN example that you can try out. It's in the examples directory, and it's called car_RNN. And as I mentioned earlier, so instead of just having the feed-forward layers, in this case, we have this temporal relationship as well. So the hidden layer at time t receives input from time t-1, and that helps this kind of network understand some temporal relationships. So we'll be looking at a more interesting example with the sentiment analysis example a bit later in the talk. So at Nirvana, we're sort of really interested in speed because we tend to deal with pretty large models and data sets. And if you want to iterate and it takes 25,000 hours to train your model, then you're not going to be able to do much iteration. Like people mentioned that they want to try different kind of hyperparameters or different architectures. So we spend a lot of effort in trying to really optimize our GPU kernels. And so that's sort of why the backend is really fast. And so we're able to get some pretty big speed ups, as you can see there. There's some public benchmarks on which we do pretty well. So for some of these models that can take weeks to train, we can train them within a day or two. So that can be pretty big speed up in terms of saving time. And these are both for ConvNets as well as for RNNs. So I'm just going to go quickly through them into the hands-on exercise. So the hands-on exercise I planned was for a sentiment analysis example using LSTMs. But it looks like not too many people are using the AMI, so again, I'll try to go through it quickly. So the idea is basically, you have some body of text. So there was this Kaggle competition using IMDb reviews, where you were given the text and you were asked to predict what's the numerical score that the reviewer assigned to that rating. And the closer you were to that prediction, the more sort of points you got in this challenge. And so that's the example I'll go through in more detail. But more broadly, you can kind of think of this as something you could apply to those other domains that I mentioned. So for example, if you're doing like medical diagnostics and you can sort of feed the medical record into a similar kind of network, into this kind or the kind that Francois described, and you can ask it questions like, does this patient have disease X? And it sort of raises some really interesting kind of applications and possibilities. So even though this is a pretty sort of concrete example, there are lots of different applications for these techniques. So there's a little bit of data pre-processing that happens in this model. Very similar to what was described in the earlier talk. So we take the words and we convert them into a one-hot representation. We use the top 50,000 words. We have special characters for pad and out of vocabulary and the begin of sentences. The IDs are based on frequency, so we use the top occurring words. We could get better by sort of taking out some of the words that don't carry so much information. And we have a predefined sentence length. And the targets are binarized. So IMDb has ratings from 1 to 10, but in this case, anything above or equal to 7 was treated as positive. Anything below that was negative. So we also have this concept of embedding in this model where you're taking that one-hot representation that's very sparse and then converting it into a more dense representation. And these representations have interesting properties. So similar to the example with the foreign languages, you can do kind of interesting vector math on the representation of these different words. So it learns this relationship between the gender of different words. So if you take the vector representation of woman, and then subtract it from man, and add in uncle, you would get the vector for aunt. So you can do these kind of interesting vector operations with the representation of these words. So in this case, the model looks like this, where the first layer is an embedding layer, where you're going from that one-hot representation into a dense representation. The next layer is an LSTM layer, so it has 128 LSTM cells. And all of that sort of feeds into a recurrent sum layer, which sort of sums the output of those LSTM cells. And then finally, there's an affine layer, which determines whether the review was positive or negative. So if you have access to the AMI, or you can even go to GitHub and look under examples for the IMDb LSTM example, you'll be able to see some of the components of the code that I'm going to go through in the next few slides. And after that, I can actually run it and show you what that looks like. So all or if you want to go ahead and run it right away, that's the command you would use. So that's basically running the IMDb LSTM script. It's saying use the CPU backend. You could also tell it to use the GPU backend. Although for now, we're very focused on the Maxwell GPUs, but we'll be bringing in support for the Kepler GPUs, which are on AWS in about a month or so. So for now, if you're using the AMI, then I suggest using the CPU backend. The E specifies how many epochs you want to run your model for. So in this case, it's just going to train for 2 epochs. And it turns out that's good enough to get really good performance on this model. The val says how often you want to display the validation data set. So typically, when you're doing machine learning, you want to have some kind of validation data to tell you what were your best parameters. And the R is just setting your random seed. So you get some kind of reproducibility across different runs of your model. But you could also change that in order to get different models that you could then ensemble to get an even better prediction. So in the code itself, it starts off with specifying this backend. So if you want a CPU or GPU backend, and then there are these different fields going to initializing the backend, like which device you want. Like if you have multiple GPUs on a box, what the batch size should be, and what the seed should be. Another thing I forgot to mention was that we also have support for 16-bit floating point, because sometimes you're running your models on GPUs with 4, 8, or 12 gigabytes of memory, and that can constrain how big your model can be. But you can go into these lower precision numeric representations to be able to get effectively more memory out of that device. So that's a way to fit in larger data sets and larger models. So the next thing is loading the data set. So in this case, we have this load text command, which can load different text data sets. In this case, the IMDb one. And then there's this pre-processing step of padding the data, just to make sure that all the sequences are of the same length. And then they get fed into this data iterator class, which basically makes them into this data set class object. Then there's weight initialization. So in this case, the embedding layer is initialized with a uniform initializer, whereas we also have a glowdot for some of the other layers in the model. And then it finally comes together in the architecture of the model, which in this case is the embedding layer, which is the lookup table layer, and then the LSTM layer, the recurrent sum layer, dropout, and then affine. So dropout, as you heard before, provides some degree of regularization for these kind of models. And then the specification of the cost. In this case, we're using multi-class cross entropy. And the metric we use is accuracy. And then finally, instantiating the model. So the optimizer in this case is AdaGrad. It's initialized with those parameters. And then we have this concept of a callback in order to, you can do sort of various functions with it. In this case, we're going to use it for reporting the error on the validation set. But we're also using it for logging, and the output from the logging can actually be fed into a visualization framework that we have called NViz, and the details of that in our documentation. So the visualization is actually pretty interesting, because then you can start doing some of these debugging things, like looking at, have the weights converged, do the filters look like something reasonable, and things like that in a convolutional kind of setting. And then finally, we call the model.fit function that takes in the data set, the optimizer, the number of epochs, the cost function, and the callbacks. So yeah, so these are sort of the things that were planned for the tutorial. Let's see. Is anybody interested in doing this, or? Yeah, okay, cool. So, so if you go into your Neon folder, if you git checkout tutorial, so you're on the tutorial branch, and activate your virtual env. So you, let's see, I'm already in my virtual env, but you would basically do .bnv bin activate, like that. And then hit enter. And if you have your favorite text editor open, you can look through the, so there's a README file in that directory, which kind of goes through some of the instructions that I'll be going through, some of the commands. There's one additional step, which is to copy the training set over into that directory. So if you can run this line, it'll copy the training data, which is in this Neon Workshop IMDb label train data directory. IMDb directory, and it's called label train data.tsv. Just copy it into your Neon directory. Sure. Yeah. So once you've copied that over, we can quickly go through the prepare script, but basically it does this one-hot encoding of the data, as was mentioned in the previous talks. The basic idea is you take the text and convert it into these vectors that have basically all zeros except for one for the position where the word is. So we can quickly run that line. So you can try to run this line. To just display some statistics about the data, like the vocabulary size, the number of samples, in this case 25,000 examples, the number of classes, and the distribution. So that's done. So the next step will be training. So the training is in the train.py file, and it's basically contains what I just showed you guys on the previous slides, which is the backend and loading of the data set, initialization of the weights, and the different layers, and the fit function. So we can quickly run that as well. So if you're running it on the AMI, you'll want to run it without the GPU option. So it'll be the second, it'll be this version of it. So I can also run that. So it's going to go ahead and apply the AdaGrad optimizer and use the training data set that was specified to start training the model. It doesn't like the resized line, so let me just restart that. All right, so that's better. So yeah, again, it gives you the summary of what the network looks like, which is basically has a direct correspondence into the layers that you specified into building that model. And this is going to go ahead for, it's probably going to take about, it's under examples/IMDb. So in the interest of time, I might just go ahead and show you what the inference part looks like. So in the inference part, you're using the model that was trained. So in this case, in this directory, I already have a trained model that's stored here in a pickle file. So I'm just going to call the model and then feed it new examples from IMDb and ask it to predict what is the sentiment positive or negative. And if you're sort of running this model, you can let it run, let it train, and then sort of have fun with entering in your own favorite movie reviews, or you can copy some from IMDb just to see how it works and where it works, where it fails. But I can show you a couple of examples right now. So let's start the inference. And in the Neon Workshop /IMDb directory on the AMI, there are a couple of text files called example good and bad. So you can actually go into those files and copy the sample reviews and sort of see for yourself what the performance looks like. Here's a review that was from the movie The Matrix. And these reviews tend to be pretty long. People have strong feelings about their movies. So it starts off by saying it was a very exciting summer blockbuster, visually fantastic, but then towards the end, there were a lot of things that the person didn't like. So in the end, it was a disappointment, and 4.5 out of 10, which should be a negative review in this case because it's less than 7. And the algorithm predicts that correctly so in this case, 0 is, so the first one is a prediction for the negative review, or the probability that it's negative, and the second number is the probability that it's positive. So it had a much higher probability that it's negative, indicating that the model thought that this was a negative review. So so there are a lot of fun examples in the file, so I'd encourage you to play around with it. I can also show you an example where it didn't work. So here's another one. In this case, it was a positive review, but the algorithm gave the negative option a slightly higher score. But overall, this model is able to get close to, I think, close to 90% accurate. So it's pretty impressive that you were able to go straight from raw sort of word input to sentiment with such a small model. So any questions about that? Or? Nope. Okay. So in the next part of the talk, I had a short demo. So this relates to this deep reinforcement learning model that was published earlier this year in Nature, where the same kind of model was able to learn, I think, 50 or so different Atari video games. And it was able to learn those by looking at just the raw pixels and the score that a human would see, basically, when learning such a game. And it wasn't given any heuristics about what the objective of the game was. It had to learn that from the pixels themselves. So this was a contribution by Tambit Madison from Estonia. And his GitHub repo is there. So he used Neon for the deep Q network part of the model. So this model actually is fairly complicated. It has many different components, of which the deep learning part, or the deep Q network part, is one of those components. And that's the component that learns this mapping from the state of the game into some kind of score. And there's another component which is called the replay memory. So as the game is playing, they remember what kind of moves were made and what the difference in score was as a consequence of the move. And they store that in a memory which they can use they retrieve from the memory as they're training this model. And this helps them remove correlations in the observation sequence, which is one of the issues with sort of standard reinforcement learning. Another new thing they did in this was to freeze the target network that they were trying to learn. So in these reinforcement learning models, you're using the deep network to predict a score, but then you're trying to get an error, essentially, and to get that sort of ground truth for that, they use that same network but frozen in time at every 10,000 epochs or so. So it's a little bit counterintuitive that sort of yields the best kind of model, but it seemed to work really well for them. And then there were a few other tricks, like they clipped the scores between -1 and +1, so they didn't have to change the learning rate across the games. And as I mentioned, the same kind of network could play all these different games. So, I mean, this is essentially the algorithm. It's, again, kind of getting close on time, so might have to skip it, but feel free to ask me offline. And then this is basically what the games look like. So, the network could learn to play Pong really well, and then also a game like Breakout. And yeah, so there are actually examples of this on the AMI as well, but we ran into some issues with the Amazon Linux. But if you have Ubuntu, then if you follow the instructions, it should work. But I can demo it sort of briefly here. And this is what the deep Q network looks like. It's very simple. It has 3 convolutional layers, a couple of affine layers, and then the final output is the predicted change in score as a result of making that state. So there are 4 outputs, one for each action that you would make in that state, and the network is kind of outputting whether that's going to lead to an improvement or a reduction in the score. So that's the Neon code for that. It's like 6 or 7 lines of code to do the deep learning part. And if you look in that repository under the source directory, there are maybe 4 or 5 other files that implement the different modules that I mentioned earlier. So there's a main executable, and then there's the agent.py that has the agent class that does the learning and the playing of the game. There's an environment.py, which is a wrapper around this thing called the arcade learning environment, which is another open source project that provides the gameplay for the Atari video games. And then there's a replay memory.py, which is the class that sort of provides the replay memory. So I can just sort of quickly go through what this demo looks like. So I tried it a little bit earlier, and there was a little bit of latency because I was trying to connect to some servers that are not here, but I think it'll convey the idea of sort of what's going on. So if I was training the model, I would basically run these commands. So it's just there's a train.sh shell script, and you provide these ROMs for the different games. So if I was training Breakout, I would train with the Breakout ROM, and if I was training Pong, I would train with the Pong ROM. On the machine that I'm connected to, I've already trained the network. So with a GPU, it took about 3 days or so to finish about 60 epochs of training on Pong. So let me show you what the model learned. So because there's so much latency, I'll just go straight to the already trained model. Otherwise, I would have shown you kind of initially that let's actually try it. Let's start with the beginning. And see what the model looks like initially when it's only had 1 epoch of training. So this is the okay. So if you're running it sort of closer to the server, it would be running much faster, like in the videos, but you'll get a little bit of a sense for what the model has learned. So here it feels a little bit like in slow motion. But you can see it's basically, in this case, not even moving, because it hasn't really figured out what the objective of the game is. So let's look at a more trained network. You can see now it's actually moving around, and at least it got the ball, and I'd encourage you to try it out on your machines once you get back home, and you'll actually see it running much faster. And sometimes it looks like it's sort of become conscious, but I can assure you it hasn't. It's just math, and it's kind of learned the structure of these games, but it's not going to take over your toasters or anything anytime soon. So I'll let that play, and I'll come back to it, and we can kind of check on the score a little bit later. So just a couple of words about what we're building up to with Neon. And so we're going to have this cloud, which we have in private beta right now, where the idea is that you have your script, which you can run locally on your desktop or workstation or your laptop. And then once you're ready to kind of scale up and you want to make a bigger model or try it on a bigger data set or even on a smaller model, you can just change one line and submit that model into our cloud. And things will just run sort of faster and in a more scalable way. And so we have a basic set of tools that allows us to do that, and we use it internally to solve our customers' problems. So if anybody's interested, you can contact me offline, and we can discuss it more. So yep, that's pretty much it. That's my email address and Twitter, and our GitHub is on github.com/nirvanasystems/neon. Also encourage you guys to check out the DQN repository from Tambit Madison, and want to thank the team at Nirvana who came up with all the code and the demos as well. Everybody works really hard to do a great job, and we love to hear more feedback. So if you guys have any suggestions or any questions, please don't hesitate. So, thanks a lot. Any questions? Nope. Cool. Nope. Yep.
About any possible real-world applications you figured out implement so far, or you just do sort of demos for now?
We're still in early stages, but we are exploring some areas like looking at trade execution for finance, for example, and there was also some interest in sort of using them for improving security, so modeling intruders and things like that. Yeah. Anybody else? No? Nope? Yeah.
Did you try training with 16-bit?
Yes, yeah. We have an example for AlexNet that we trained with 16-bit, yeah.
What? It's great.
Yeah. So the D-type parameter basically changes. If you provide it initially, it would change it for all the tensors in the model. Okay, great. The computer is winning, so it's 2-1. A good point to stop. Thanks. What's that?
Temperature?
2-1. Sorry, the score was 2-1 in favor of the computer. Can you just put this there? Yes.